Hey, welcome back. I'm checking on our audio and video. If anything came up before, sorry about that if I just disconnected it. Now it seems like it's working. I just need my... Okay, we have audio, we have video, we're ready to jump into some rocket science, looking at numerical methods, specifically integration methods, so like implicit, explicit, differential equation integration, and some root finding methods of like, now that we have a model, it seems to work, it's verified, or we haven't really, usually validation has to do with using experiment, like something measured, and then you can compare it to that. All right, so we'll pop into CompMech 03, close all these, come on down to project number 3. So this project, this is an exercise in like building a model where we know what forces are involved. It's rocket science, so it's not a simple problem. There is a simplified rocket solution, a rocket science solution made by this guy Tsiolkovsky. And what he figured out is that if the thrust is much bigger than gravity and drag, then you have a direct relationship between how much mass you use in fuel and how fast you can go. Pretty helpful. In reality, if we're sending a firework into the sky, gravity is very much a factor and drag is very much a factor. Like, we want it to go fast, and so that force is going to be big. So it's a two-step process. Well, kind of 3 steps. The first step is making sure that when we do numerical integration of this equation, it matches this result. So that's the first step. Once we've done that, we've verified that the numerical integration that we're using, it works. The next step is add these other terms to it. So add some gravity, add some drag, and then integrate in 2 different ways, both with an implicit and an explicit, and see if there's any difference. If both of them are converged to the same thing, then we know that the effects of gravity and drag are independent of that integration method. Then the last step is that since we have a model that works, now we can start using it to make predictions and optimize things, and we'll figure out what is, coming down here, what mass rate should we use, this DMDT, so that our rocket reaches 300 meters when it runs out of fuel. And that's it. That's what we're trying to do. So a couple of steps, verification and all that. All right, cool. So how do we get started? First, for every integration method, we need a differential equation. And I saw some different ways of creating this simple rocket equation. Like, some people removed all of this, all the doc string, and just made like a function there. One thing I did want to point out, that some people, you've been like redefining this function. So there's like a def simple rocket up here, but then inside of the integration method, there might be a new simple rocket defined there. That can get really confusing really quickly if you have competing functions that are the same or maybe slightly different, because you'll change one, but the other one's the old version, and when you try to run things again, it'll mess with the way things are. That happens to me all the time, especially with variables. Whenever I have time labeled as the variable t over and over, then I end up with like conflicting values of t that have different sizes and different length, different values. Things get confusing. So best practice is that if you have a variable called simple rocket, it's always the same. Like, it's in one block on its own, and just leave it as that. If you don't like the way this is set up, you can delete whatever you want and then define it down here. But I'm going to do it my way because it's me. I get to do it my way, right? All right, so D state, the change in my first state. So the state consists of height, speed, and mass. So the change in height is the speed. So it's state 1. Another way that sometimes I like to do this is say state or y the mass is the state. This is called unpacking the variables. So let's say I have an array of 1, 2, 3. I could say A, B, C are 1, 2, 3. And then if I look at what, oh yeah, it would help to run that import numpy, right? So if this array has 3 values in it, like height, speed, mass, so 1 meter, 2 meters per second, 3 kilograms, then I can assign all 3 variables to those all at once, as long as it's the same size. Like if I try to do this, A comma B is that, it'll give me this error that, hey look, you expected 2 because there are 2 on this side, but that's not right. Like there are 3 things inside of here. So sometimes I like to do that so that I can say the change in y is v, and then the change in v is, I'm just going back up to the original differential equation, dv dt is u over m times dm dt. U over m, and m, remember m is part of this state now, times dm dt. And I could have grabbed it from this documentation, but I like to double check. Stuff. All right, and now d state of 2, that is the change in my mass over time. And the main tricky point here is just this has to be a negative dm dt. That if dm dt is creating this amount of thrust, then my mass is losing that amount of mass. Just keeping the signs consistent. All right, so now I've got my differential equation. I can say simple rocket of, given an array, and we could try just 1, 2, 3. And I get, if I'm moving at 2 meters per second, my change in height is 2 meters per second. If I'm 1 meter up, moving 2 meters per second, and my mass rate is this, then I have an acceleration of 4.17 meters per second. 3 kilograms is losing 50 grams per second. So 0.05 kilogram per second. And make this like 20. And what we can see here is that no matter how fast we're moving, we still get the same kind of values, because the only thing it really depends on is this U, so how fast we can burn things, and so that speed of the propellant, which is limited by the chemistry of how this thing burns. M is the current mass of the object, and then that dm dt, that's like how big of an opening your rocket might have. So that's the main control variable that we have. We can change the opening and make it burn faster or slower. So it works. It's giving, if I give it 3 inputs, it gives me 3 outputs. They're all derivatives of those inputs. And let's keep everything in here. So I set up some initial code here to try to help. It might also have confuse because sometimes it's more confusing to like debug someone else's code. But what this is giving us is an initial mass, a final mass. So I'm gonna burn 1/5 of a kilogram, 0.2 kilograms. So my final weight is 50 grams. My initial is 250 grams. And I'm losing 0.05 kilograms per second. So that means time is going to start at 0 seconds and go until that dm/dt over the 0.2 kilograms divided by dm/dt kilogram per second is it is at its final value. So once I've burned that 0.2, I'm splitting it up into 500 steps, but this can be any number I want. I could say 11 if I wanted. And then dt is the time step that I'm actually taking. And since I'm integrating, let's use some of the integration methods that that were in the readings, just to get some practice, like identifying like what are these different methods and how do we use them. And the Euler step is kind of our simplest one with the worst convergence that we found. Euler-Kromer was a little better convergence, like a second order convergence. And that one would work. So let's try that one. I'm just going to put it above. And again, once I define it, once I run that function, now I can use it anytime I want. So in this step, what I did was initialize time, of saying like, this is my independent variable. It's going to start at 0. It's going to end at 4 seconds. In this case, it's 4 seconds. And it's going to take 11 steps to get there. Now I can say my state is np0s, and I want it to have length of time. So I want it to have 11 rows and 3 columns, because I have height, speed, and mass here. My initial state is 0 height, 0 velocity, 0.25 kilogram per second. Or I could say m0, like that. Now, every other state I'll define based on that current state, or based on this initial state, sorry. So I'll start at 1, go to the length of t, and now state of I, so state 1 is 1 Euler-Kromer step of, so I think I do state, then the right-hand side, then dt size. So state, so it's going to be based on state of I minus 1. My right-hand side is simple rocket, and my step side, my time step is dt. And number of rows. So it can't broadcast 2 to 3. Why not? I missed something along these lines. So my simple rocket, I thought I was using it, right? Oh, this might be the one that it gives me, yeah. So this one is expecting just a 2 value thing for this Euler-Kromer, because I'm manually creating this next state by saying this array is the speed plus the acceleration times time. All right, so I can't use Euler-Kromer. And that's why I wanted to go through this, was just try troubleshooting one of these kind of manual integration methods. So let's go down and find a different one. We'll use this modified Euler, this Runge-Kutta 2, and we'll get rid of this Euler-Kromer. So Runge-Kutta 2 is it's still a second order convergence method, but instead of manually creating that next state by grabbing individual states there. This one, it's agnostic. It doesn't care. Like this could have 40 values in it, or it could have 2 values, or it could just have 1, but it's just as long as the state and the function of the state have the same size, we can multiply things, add them together, and end up with a result. So instead of Euler-Kromer, let's do our RK2 step. And now we end up with 11 values of just numbers. And again, like we're not finding functions with all these numerical methods. That's why we end up having to use like root finding methods to actually get to results that we can use. But I can look at, and again, coming back up to my state is height, speed, mass, and that Tsiolkovsky solution relates speed and mass. So I could say M, the state, if I take all the rows of column 2 and all the rows of column 1, plot those as like circles. Now I have this plot that when I'm at my initial speed, and if I want a relative value, I could divide by that M0. So when I'm at 100% of my mass, I'm moving 0 meters per second, but the more mass I burn, the faster I move. And again, this is ignoring drag and ignoring gravity, but it's a good starting place here. And the question is, are these dots lined up with this Tsiolkovsky solution? Because for this differential equation, this is an exact solution. It's not physically accurate in our case. It might be physically accurate in deep space, but here it's not the case. So let's take a look at how I could compare those. So mass goes from 1 to 0.2. We'll call it like MT is np.linspace of 0.2 to 1. V Tsiolkovsky is going to be a function of that mass. And let's go back up. And sorry to scroll back up and back and forth. But it would be the log of mass over the initial mass times negative u. So negative u times the log of m sub t over m0. And u is not defined, so let's define it. I think u is 250. Maybe it's not. What is it? U is 250. Oh, yeah, it would help. It would help if I kept things in the same. So this is times m0, like that. Keep them in. So let's undo what I just did. Get back to this plot. So I've got these two plots. They're not the same. Very much not converged. They don't even look like they would converge at this point, at least from my perspective. Like, I don't think this 400 is actually a 100, and I don't think this 0 is actually a negative 300. So convergence aside, something's wrong with this plot. So when I said mass goes from 0.2 to 1, really I was saying the relative change in mass goes from 20% to 100%. So if I want the actual change in mass, I want to say times m0. So that's better, but now these x-axis scales are different. This one goes 1 to 0.2. This one's going like 0.25 to 0.05, which is the actual mass. So I want to take that, divide it by m0. And you might have like different issues, but if you're looking at lines and they're like completely separate or they're off by a lot, then there might be something weird going on. All right, these look like they are the same. And let's go back up here. So we said there were 11 states. So we could make the same. So plotting these, like these 11 states, this looks really good, right? And if I make this even smaller, make it like 7 and 7, it's still really good. Like we're converging. It's going to be a little bit different, so let's look at that 400. Let's take these. And now I can see what the error is as a function of that 0 point, as a function of the mass. Like here's 100% mass. Why? Should be. Oh, it's flipped. So this should be much closer to 0. So what I want to do. So right now, because this is time 0 moving this way, but this line starts at 0.2 and moves that way, I want to take all the states backwards. Well, I want to take all these velocities, start at the same point, but move backwards through them. And now I can see like start at 0, and then it becomes like -4. So I'm off by 4 meters per second by the time I get to that 400 meters, which is not very far off. But if I make this 1001, oh, that one shouldn't matter. Let's make that. Let's define both of these as n. So I don't have to keep changing it back and forth. Now all the dots look pretty close, and if I look at these, it's still increasing in error. And that's usually what we found with explicit methods in general, is that over time you'll get a little bit off. You're always going to like increase error as you move over time. Even with implicit methods, they'll increase somewhat, but not as much as explicit methods. And yeah, it would help to add like titles and X labels and all that, because this one I'm looking at error, this one I'm looking at like actual values, comparing them. But the main thing is we are converging, that I can pick a time step and converge to this exact result. And that's great, because that means that I have verified this integration method, that I can use this to solve differential equations in rocket science. So if I make the equations more complicated, they should converge in the same way. There might be other things that change a little bit, but for the most part, it'll be the same. And let's just grab, since I did all that work up here, I'm going to do the same thing down here. YVM is state. let's just grab these two. So I want to do that, paste those two down here, delete that. I'll merge these two. All some fancy, just like Jupyter reorganizing stuff. So instead of simple rocket, I'm going to use rocket. Well, do I want to compare both? I already calculated state, so let's call it R, like rocket RK2. RK2, RK2, and RK2, RK2, and actually I do want to grab this value, plug it in again. This one will be red, that one will be blue, this one will be a black line to compare everything to. And right now, all I did was take the code that was working and used it again. That's not what I wanted to do. I wanted to add those other things, but I forgot. So, but now I know, like, okay, I define new variables, but I'm actually solving the variables correctly. So I can use that Runge-Kutta two-step. I can integrate this thing. Now I can start adding subtract gravity and subtract the C over M times V squared. So I add gravity, add drag, run this again, and nothing happened. Something should have happened, right? Arv RK2, use that RK2 step. Oh, I'm using state. R RK2, like that. That would help. All right, there we go. Now I'm seeing an actual change due to gravity and drag. And this step is important because as you make small changes, like sometimes they have the effect that you expect, other times they have an unexpected effect. Like the fact that this almost looks like a straight line seems weird, like in a rocket science kind of thing. So how do I figure out, like, is that because of my integration? Like, am I doing things wrong, or am I actually doing things right? So one way is that down here where the mass hasn't changed very much, I can see that everything is on the same line. So it starts to diverge the faster I move. So as speed increases, I start moving away from this. That makes sense based on this differential equation where I have this term where the bigger speed gets, the less I can actually accelerate. So in that sense, that's one way I can kind of convince myself, like, okay, this makes sense, that like a rocket can't get to 400 meters per second when it's fighting drag. Like something has to slow it down. So that's one way. Another way is I could do an experiment and say, well, if this line is when gravity and drag are zero, what if thrust is just so big that gravity and drag look like zero? So I could come in here, and because I set up my rocket equation, where I can plug in the state and this dm dt, I can increase the value of dm dt, make it like 10 kilograms per second, like almost an explosion. Oh, and problem there is that I do need to update that dm So if I want to, I need to update time. So if you're getting like weird results like this of negative speeds or something, it's because mass became negative and now like time and space make no sense. Can't really have a negative mass rocket. So instead, update this one. Let's call this one 10 kilogram per second. And now everything is directly on top of each other because it's so much bigger that way. And I could try like subtracting these if I want to look at the difference, but that's one way to convince myself that that's the case. So I'll plug this back into here, 0.05, it's different. So the other way is if I think and it could be someone could point out like, hey, maybe your integration is wrong. And that could be the case. So the best way to check that is, all right, well, let me use a different integration method. Let me go find an implicit method. So in this case, here's an implicit Hewn step. And again, the thing that makes it implicit is this iterative correction. Like it checks for convergence before it moves on to the next time step. It does not increase the accuracy or the convergence rate of the method, but it does prevent it from like overshooting at each time step. But it still has, the weird part is that it still has the same convergence rate. So for a given delta t, if you decrease it to 1/2, you get 1/4 the error. Okay, so we'll grab this, make a new cell, plug it in, and let's take all this, copy it, paste it, and HEU, take all this, copy it, and paste it, grab here, here, HEU, so it looks the same, looking good. And now I want to take this one, plot it on top of that one, and let's call these like green squares. And the green squares are right on top of the red circles, so we can't actually see anything. If we want, we could do like : 10, : 10. I think there's a lot of points, a lot of data points on here right now. There we go. So now I can see every 50th. So that : is start at 0, end at the end, and go steps of 50. So I'm skipping every 49 values and just plotting. And now I've got like a nice garland kind of ready for Christmas in July. All right, cool. It seems like we're making a lot of progress now, and I'm kind of walking through this whole thing also to like wrap up the ideas of module 3. The work that I saw from this, awesome like debugging. It seemed like there's been a lot of like great work, but this is like a nice culmination and a review of module 3 in general. So I wanted to walk through at least the way that I would do it. There's different ways to do it and other like great ways to do it. Okay, so now what I have is a function. What I have is a function that describes a differential equation of a rocket, and what I want is a rocket that explodes at a certain height. So if I know how fast I'm burning, I can calculate how high I can get. So with these, let's see, is it time, t? Yeah, I have just t defined over and over. And whether I use this RK2 or R Hewn, they're both the same. I'll look at that first value. I start at 0, go up to 425 meters. And yeah, it doesn't matter what method I use. If I'm looking at a rocket, that's the case. If I change that dm/dt, which for an engineer is like drilling a different size hole in the bottom of the rocket, now I can change how high it'll go. That'll change the mass rate. So what I want to do is look at this code, figure out what's the minimum set of things that I need in that function that it's going to return that value. So I need this converged time step. I need like the initial and final. So let me just start by grabbing kind of all this. I don't need everything. But I'll try grabbing all that and just plugging it into my work down here. And you can highlight everything and hit tab, and you can tab things and untab things. So in this case, M0 is a given value. I don't want to overwrite that. C is a given value. I don't want to overwrite that, but I don't think I am. And I only need one of these things. Rungakutta seemed like it worked pretty well. And actually, I don't really need to. I could just take steps. I'll leave it the way that it is. But one thing that I saw that was kind of clever is that you could define this as just a state of 3 values and just keep updating the values with a time step. We don't have to do, well, why don't we try it? Yeah. So instead of defining like in a whole array, I could just get the final value. So I could say that this is np.array of this. So I'm going to take that array and update it by 1 time step. And now it's not an array of like state as a function of time. It's just the current state. So I just keep updating the current state until I get to this final time, and then I'm good to go. Let's do like 101 steps instead. Doesn't really matter how many steps you take, but error is that RK2 of 0, so the final height, minus that 300 meters. And let's see if it works. $125 meters. I thought before we were saying 400. So let's go back up. Here, the last thing that I get is 425. So I could subtract 300 from this and look at, start at negative 300 at 0, makes sense. And then by the end, I'm somewhere up here at like 125. So it seems like it's giving me the right result. Oh, one thing, let's watch what happens. Let's make it 0.5, much bigger. I still get 125. Meanwhile, if I come up here and change this to 0.5, what we saw was that things are different, that it should be changing. Like now I'm burning so quickly that by the time I use up all of my fuel, I've only gotten 50 meters off the ground, like barely reach the height of a building. I mean, it's a building, it's a tall building. So the main thing that I'm doing wrong here is that dm/dt is an input, but I'm overwriting it with this dm. So I want to get rid of that, and I want to plug in that variable that I'm using up here into my equations down here. And same thing for this case. I want to say dm/dt is dm/dt. Now, when I say 0.5, I get negative 240, and that makes more sense because we ended up at 60, so 300 minus 60, or 60 minus 300 is negative 240. All right, things are looking up, and it seems to be working. I give it a value, and then I end up some other place. So I have mod secant. Then there's also like bracketing methods. I want you to try both of them, but let's just plug in mod secant just to see how it goes. So I'll ask for mod secant of my function. My step size, that one, it has to be small. How small is small? There is a point that is too small, and there is a point that is too big. Let's do something that seems small. This is kind of big though for our case, but let's try it. And then I need some initial guess. So 0.5 seems very wrong. 0.05 seemed okay. So let's try 0.05. And I get 0.06 after 49 iterations. I ended up with this final value. And sorry. I hate when people say like, oh, remember that thing that I told you a week ago? It's like, no, I don't remember. But let's look down here. What am I getting from this value? I get this optimal dm/dt, that's xr. I get this FDM of XR. I get the error, the approximate error that was left over, and then how many iterations. So if I went through 50 iterations and the F of DM is still 49, that means that I'm still 50 meters off of where I was supposed to be. So if I take this number and plug it into this result, I can see I'm exploding at 350 meters. That's not where I want to be. I want to be 50 meters lower. So what I could do is take this number, plug it in as my new initial guess, and over here, that new initial guess. But really the problem is this step size is too big because I'm looking at values of like 0.05 to 0.06. This thing's got to be like much smaller than that because I'm trying to approximate a derivative and get to an answer that way. Now after 4 iterations, I didn't change the initial condition, but I get to this value, and that final F of DM is 1.4 10 to the negative 8, much closer to 0. So now if I take this value, and there's better ways to do this, right? Like I could say dm dt opt equal, and then plus out. So I'm just assigning them to variables that I can use. So I can grab this, plug it in up here. So now my dm dt is this value. And I get the same kind of graph. And now I'm actually reaching 300 meters at the end of my flight, my time, end of time. So after 2.5 seconds, I get up there. Yeah, so that's project 3. There's some other stuff about try using that incremental search with that bracketing method in here, and then try adding like a star marker for the last detonation mark. But I didn't see a lot of problems in trying to use that. If there are issues, like you can always reach out, you can always post on the GitHub discussions about things that you might be running into. But this was my way of trying to like wrap up what we've been talking about in module 3. Next, we're moving on to module 4, which is linear algebra. So rather than looking at like nonlinear problems, so this one's a nonlinear problem and trying to find solutions for that. Now, how do we find solutions to lots of linear problems? You can do them by hand. You can always like solve for a variable, plug it into the next equation, solve for the next one. But computers are really good at doing that kind of math for us. So we'll look at some ways that we can kind of optimize our time by letting computers take over, and where they're good and where they struggle with. Cool.